Good morning and welcome to the 7th video session. In this session we are going to discuss application of Laplace transform in engineering. In this session there are three important points we are going to cover. The first one is application of Laplace transform in evaluation of some infinite integrals, then solution of initial value problems, and also solution of initial value problems with some time shifting in initial measurement. So first of all, we are going to discuss evaluation of infinite integrals. Infinite integral means an integral whose upper or lower limit contains an infinity value. So here we consider integral with lower limit is 0, upper limit is infinity. That is one-sided infinite integral. There are two steps in evaluation. The first step is conversion step and second step is evaluation step. Then we are going to discuss what is conversion step. Our aim is to compare our given infinite integral into definition of Laplace transform. Then we convert the given integral into a Laplace transform by suitable substitution or manipulation. And this entire step is called conversion step. Now the problem is transformed into a Laplace transform problem. Then we evaluate that Laplace transform using our results. That is called the evaluation step. At the end of evaluation steps, we got the solution to the integration. We will discuss this with the help of a problem. Evaluate integral 0 to infinity t sin t e raised to minus t dt. First of all, we recollect the definition of Laplace transform. Laplace transform of f of t is equal to integral 0 to infinity this function f of t into e raised to minus st dt. So when f of t is multiplied by e raised to minus st, then integration from 0 to infinity leads to Laplace transform. Here also we have an integration from 0 to infinity and a multiplication by e raised to minus t. That means here in the place of s we have 1. We use that result. So I rewrite this expression, our problem, in this form. Integral 0 to infinity t sin t e raised to minus t dt is equal to integral 0 to infinity. I put this t sin t together, t sin t. I rewrite e raised to minus t as e raised to minus st dt with s tends to 1. In the transformed domain, I change s into 1. That's all. It is possible. This substitution does not affect this integration. Therefore, this operation is valid. Now we know that this function is multiplied by e raised to minus st and integrate from 0 to infinity. That means it is Laplace transform t sin t. So this integral is converted to a Laplace transform. That is conversion step. Now we evaluate L of t sin t. Oh, this is multiplication by t. So L of multiplication by t gives this result, 2as by s square plus a square the whole square. But here in the place of a I have 1. So 2s by s square plus 1 square all square. I rewrite it. 2s by s square plus 1 the whole square. Now it is in the s domain. Now you can change s to 1. So 2 into 1 by 1 square plus 1 the whole square. So 2 divided by 2 square or 2 by 4. That is equal to 1 by 2. So this integral 0 to infinity t sin t e raised to minus t is actually an infinite integral of product of 3 terms. This need not be easy to evaluate using classical methods of integration, but just a conversion into Laplace transform gives the result in a fast way. Okay, we will do a few more problems. Second problem is evaluate integral 0 to infinity sin a t by t dt. We are familiar with this function. Sin a t by t is our sigmoid function. We are going to evaluate sigmoid function in the range 0 to infinity. First of all, we write integral 0 to infinity sin a t by t dt is equal to integral 0 to infinity sin a t by t into e raised to minus st dt with s tends to 0. This is the conversion step. Actually in this problem there is no e raised to function. I just rewrite e raised to minus st using this manipulation. But when we substitute s equal to 0, we get back the given problem. So this is valid operation. We are integrating with respect to t. Now this is nothing but Laplace transform of sin a t by t. So this integral is converted to a Laplace transform with s tends to 0. Now this is division by t, Laplace transform of division by t. Division by t is integral. So integral is to infinity. Now just hide this t. The remaining portion is L of sin a t, L of sin a t ds. I repeat, this is a property of Laplace transform. Laplace transform of division by t leads to integration. So this is division by t. So you just hide this t. Effect of this t is integral s to infinity. Now hide this t. Then L of sin at put right like this. Then L of sin at is a by s square plus a square. Now we have to integrate this. Integral a by s square plus a square is tan inverse s by a. So this integral is tan inverse s by a. Now we have to put the limit s to infinity. Then tan inverse upper limit infinity minus tan inverse lower limit s. So tan inverse s by a. But tan inverse infinity is equal to pi by 2. Pi by 2 minus tan inverse s by a is tan inverse s by a itself. Now one more operation we have to complete, that is s moves to 0. When we put s equal to 0, we got tan inverse 0 here. Tan inverse 0 is 0. So we got pi by 2. That means integral of the sigmoid function in the time range 0 to infinity gives pi by 2. We got the same result using our Fourier transform also. Actually, these type of integrals can be evaluated without much effort in transformed domain. So it is again a wonderful use of Laplace transform to evaluate this integral of sigmoid function. Now we are going to discuss the second important application, that is Laplace transform to solve ODE. Why we are using Laplace transform in solution of ODE? Ordinary differential equations are not that much easy that we have discussed in the third module. In engineering problems, it involves many special functions in the RHS side, that means R of t area. So usual methods need not be successful. In that situation, we will use Laplace transform. The advantage of using Laplace transform is so straightforward. One is, when we apply Laplace transform derivative, it is transformed into a multiplication by s. So differential operation convert to a algebraic multiplication or algebraic operation in s. That is the advantage. So whenever we apply transform on time domain, it transformed into s domain with differentials are eliminated. Differentials becomes simply multiplication. That is the use of solving Laplace Laplace transform in solving ODE. One another important important reason to use Laplace transform is that in our previous sessions we learned there are 4 different stages to solve an initial value problem. In first stage we find out the homogeneous solution YH. In second stage we find the particular solution, and third stage we find the general solution. Even now there are arbitrary constants associated with the homogeneous solution. The last stage or the fourth stage is solution of that equation, or actually finding this C1, C2, C3 arbitrary constants using initial values. It is laborious and it is time consuming operation, but Laplace transform is a solution to this issue. Now we move on to an algorithm to solve ODE using Laplace transform. As a step 1, we apply Laplace transform on both sides of the given ODE. In step 2, we substitute the initial values and solve for y bar of s. That means you get y bar of s in the left side and put all other things into the right side. And finally apply L inverse on both sides. Now remember, after second step, in the left side or left hand side we have y bar of s. Just the application of L inverse leads to y bar s to y2, y of t. When I apply L inverse on y bar of s, this y bar of s is changed to y of t. That means that differential equation is solved. The right hand side we have to apply L inverse using the basic results or some properties that we have previously discussed. Okay, we explain this algorithm with the help of a simple problem. As an example, I consider the initial value problem y double dash minus y is equal to t with initial conditions y of 0 is equal to 1 and y dash of 0 is equal to 1. Now we are going to apply Laplace transform method. As in the first step, we apply Laplace transform on both sides of this ODE. I rewrite y double dash minus y equal to t. In order to show that this is a function of t, I put the argument y double dash of t minus y of t is equal to t. It is not necessary, but for completeness I put like this. Now apply Laplace transform on both sides. So L of y double dash of t minus L of y of t is equal to L of t. Now we apply the result on Laplace transform of y double dash. Look into this expression, it is contains second derivative. So the Laplace transform start with s square into y bar of s minus, now power of s decrease by 1, that is s raised to 1, that is s into second time is always associated with the y of 0, so s into y of 0, again minus power of s decrease once more, that is s raised to 0, that is a constant, into this y dash of 0. Whenever this s is reduced to a constant, that is 1 here, that operation is over. Laplace transform operation on this y double dash of t is over. So this much operation happens on y double dash of t. Now minus L of y of t. We apply Laplace transform of y in time domain, so it changes to y bar of s. The next step is also right hand side L of t is 1 by s square. L of t raised to n is n factorial by s raised to n plus 1. Here power is 1, so 1 factorial divided by s raised to 1 plus 1, s raised to s square. Now we club the terms of y bar of s together. I take y bar of s together, here y bar of s, then the remaining thing is s square minus 1, s square minus 1. Also we put initial conditions. Look, here y of 0 is equal to 1. Here we have y of 0. So s into 1 minus s, that's all. Now we choose y dash of 0. Y dash of 0 is here, it is again 1, so minus 1. So this term becomes minus s into 1 minus s, minus 1 into minus 1. So I can take in minus common here, so minus of s plus 1. So this expression s square minus 1 into y bar of s minus s plus 1 equal to 1 by s square. Now we put this term minus of s plus 1 to the right side. Here this s plus 1 is subtracted in the left side. So when we put this minus of s plus 1 into the right side, it gives plus. So s plus 1, this s minus of s plus 1 becomes s plus 1 here, plus 1 by s square. Now we have a square minus 1 associated with this y bar of s. This s square minus 1 is also known as subsidiary equation for this Laplace transform. Now we move on to step 2, that is solve for y bar of s. I already told you solve for y bar of s means we try to make the left side y bar of s and put all other things into the right side. We are doing it. So y bar of s equal to, we bring this s square minus 1 to the right side. Here we multiply y bar of s by s square minus 1. When we put s square minus 1 right side, it become in denominator. So s plus 1 plus 1 by s square, the whole divided by s square minus 1. Next step is we make it simplify the right hand side with the help of simple intuition. We know that s square minus 1 can be factorized into s plus 1 into s minus 1. So when we took this term together, we can cancel one s plus 1 from that term. So I put like this, s plus 1 divided by s square minus 1 plus 1 by s square minus 1, or 1 by s square into s square minus 1. Now I factorize this. S square minus 1 is s plus 1 into s minus 1. That s plus 1 and 1 s plus 1 numerator get cancelled. So 1 by s minus 1. Now I again use that tricky method to split into partial fraction. Numerator is 1, denominator contains 2 factors, and their difference gives a constant. So the idea is minus of 1 by difference between these two terms, that is 1, 0 minus minus 1, that is plus 1. So minus 1 by 1 minus. Then 1 by first factor, 1 by s square, minus 1 by second factor. Then we multiply this entire expression in the bracket by negative. So minus of 1 by s square here, minus of minus 1 by s square minus 1, that is plus 1 by s square minus 1 here. Actually we try to simplify this expression into simple proper fractions. Then only we can apply L inverse in an easy way. Now we have y bar of s equal to 1 by s minus 1 plus 1 by s square minus 1 minus 1 by s square. Now we can calculate L inverse without much difficulty. The last step, that is step 3, apply L inverse on both sides. Apply L inverse on both sides. That means L inverse of y bar of s equal to L inverse of this term plus L inverse of this term minus L inverse of last term. I did it here. L inverse of 1 by s minus 1 plus L inverse of 1 by s square minus 1 minus L inverse of 1 by s square. The left side L inverse of y bar of s is y of t. Then we know that L inverse of 1 by s minus a is e raised to at, and therefore L inverse of 1 by s minus 1, here a is 1, e raised to t, plus L inverse of 1 by, this is a square minus 1, so sin h function will be there. Here a is 1, so 1 by 1 sin h 1t or sin h t, minus 1 by s square. We know L inverse of 1 by s raised to n plus 1 is t raised to n by n factorial. Here n plus 1 place is 2, so n is 1, so t raised to 1 by 1 factorial, or t raised to 1 by 1, or t. or in effect we got the solution y of t equal to e raised to t plus sin ht minus t. See, the advantage of using this Laplace transform in solving ODE is that we need not to do many steps. In a single stretch we got the solution. There are three distinct steps. Step 1 is apply L inverse on both sides. Apply Laplace transform on both sides. Then substitute initial conditions. In step 2 we solve for y bar of s. That means we make the y bar of s the only term in the left hand side. Then only we apply L inverse of y bar of s leads to y of t. So solve for y bar of s. The last step we simplify the right hand side, then apply L inverse on both sides. So left side is y of t, that is our required solution. The right side is automatically gives a function in t. That is the idea of solving ODE, or more precisely solving initial value problem using Laplace transform. We will do one more problem. In this problem, y double dash minus 3y dash plus 2y is equal to 4 e raised to t, and y of 0 is minus 3 and y dash of 0 is equal to 5. Here both second derivative and first derivatives are present. As a first step we apply Laplace transform on both sides. So here y double dash, so we start with s square into y bar of s minus, we decrease the power of s by 1, that is s, into second term always goes with y of 0, minus decrease power of s by 1, here s raised to 1, now s raised to 0, that is 1, into next term is y dash of 0. So Laplace transform y double dash is over. Then minus 3 into, then remember we have to put a bracket here, minus 3 into Laplace transform of this derivative y dash, that is first order derivative. So s into y bar of s minus decrease the power of s by 1, so s raised to 0, that is 1. Then the second term is always y of 0, close the bracket, it's over, plus 2 into y bar of s is equal to 4 is a constant. Laplace transform of e raised to 2t is 1 by s minus 2, so 4 by s minus 2. Now you just club terms of y bar of s together. Y bar of s into, here we have an s square, here I have minus 3s, s square minus 3s, here I have 2 plus 2. Then substitute the initial values. See, I fix y of 0 equal to minus 3 first. Then wherever we have y of 0, here we have a y of 0 and also here. Y of 0 equal to minus 3. Minus 3 into minus s, that is plus 3s, plus 3s. Then minus 3 into, here minus 3 into minus plus 3 into minus 3, minus 9. So y of 0 is over. Next is y dash of 0. Here we have a y dash 10. Put this 5 here. So minus 5 is here. Then simplifying this expression, 3s minus 14. So finally s square minus 3s plus 2 into y bar of s plus 3s minus 14 equal to 4 by s minus 2. As in the previous case, we bring this entire term to the right side, that is 3s minus 14 to the right side. Here the entire term is plus. When we put that term into the right side, it is negative. So negative of 3s minus 14. See, 3s minus 14. This is our subsidiary equation. Now next step we are trying to solve for y bar of s. That means we try to make y bar of s on left side and put all other things on the right side. That means y bar of s equal to, we divide the entire terms on right side by this s square minus 3s plus 2. So 4 by s square minus 3s plus 2 into s minus 2 minus 3s minus 14 divided by this s square minus 3s plus 2. The next step is simplifying this expression using partial fraction technique. For that I take the first one, then second one, then make it partial fractions and diffuse together. Here note that s square minus 3s plus 2 can be factorized as s minus 2 into s minus 1. So in this term we have s minus 2 and s minus 1. So s minus 2 and s minus 2 is s minus 2 square. The remaining one s minus 1 is here. And again we factorize this in the denominator, s minus 2 into s minus 1. First of all, I take this expression. For convenience, I put this 4 by s minus 2 the whole square into s minus 1 in RHS. Then I write it as partial fraction form, a divided by base form of s minus 2 whole square. Base form of s minus 2 whole square is s minus 2. So a by s minus 2 plus b divided by next power s minus 2 the whole square plus c divided by the next factor c by s minus 1. Now we multiply both sides of this expression by the denominator s minus 2 the whole square into s minus 1. So the expression becomes 4 is equal to a into s minus 2 into s minus 1 plus b into s minus 1 plus c into s minus 2 square. Next stage is elimination of elimination of these constants to find some constants a, b and c, etc. For that I put s equal to 2 first. Here we have s minus 2, here also s minus 2. When we put s equal to 2, this term 0, this term 0. So b into 2 minus 1, that is b is equal to 4. We got b is equal to 4. When we put s equal to 1, we got c equal to 4 like this. So there are only 2 and 1 involved in this expression. Then we have to find out a more. So the best way is to equate the coefficient of s square on both sides. Here coefficient of s square is a, here coefficient of s square is c. That means a plus c here. In the right side we have 0 because no s square term. The coefficient of s square is 0 there. So 0 equal to a plus c. Answer therefore a is equal to 0 minus c or minus c. But c we have 4. So a is equal to minus 4. When we substitute a is equal to minus 4 here, I got minus 4 by s minus 2. B is equal to 4 here, 4 by s minus 2 the whole square. Then c is equal to 4 here, 4 by s minus 1. Okay, so we got the partial fraction. This proper fraction is divided into 3 simple fractions. Now we repeat the same thing on the second term, 3s minus 14 by s minus 2 into s minus 1. I represent it as a by the first factor plus b by second factor. Multiply both sides by the denominator of the left hand side. I got 3s minus 14 is equal to a into s minus 1 plus b into s minus 2. Now we apply elimination. I put s equal to 1. So we got a is equal to 0. A part is 0. So b into 1 minus 2. That is minus b is equal to minus 11 or b is equal to 11. Similarly I put s equal to 2. So here 2 into 3 6. 6 minus 14 that is minus 8. When we put s equal to 2 here, 2 minus 2 got 0, so b term eliminated. 2 minus 1, a is equal to minus 8. The next step, we put a and b here. A is equal to minus 8, b is equal to 11. So we got 3s minus 14 by s minus 2 into s minus 1 equal to a value minus 8 by s minus 2 plus b value 11 by s minus 1. The next step, this is the RHS of our y bar of s. I write the RHS and diffuse both these terms together. So minus 4 by s minus 2 plus 4 by s minus 2 square plus 4 by s minus 1. That is the partial fraction corresponding to this expression. Now for minus of, that minus of is important. This minus of minus plus 8 by s minus 2 minus of this plus 11 minus 11 by s minus 1. There are some like terms. Simplify this. S minus 2, s minus 2. So minus 4 plus 8, 4. S minus 2 square, there is only one s minus 2 square term in the denominator. So 4 by s minus 2 the whole square. Then 4 by s minus 1 and minus 11 by s minus 1. When we are adding these numerators, we got 4 minus 11, that is minus 7 by s minus 1. So the entire RHS becomes these 3 simple fractions. So y bar of s equal to our 4 by s minus 2 all square into s minus 1 minus 3s minus 14 by s minus 2 into s minus 1. This entire expression can be simplified like this. I substitute it. So y bar of s equal to 4 by s minus 2 plus 4 by s minus 2 the whole square minus 7 by s minus 1. Now we can take L inverse of RHS without much difficulty. So move on to the last step, taking L inverse on both sides. L inverse of y bar of s equal to y of t. L inverse of this expression, 4 is a constant, take it outside. L inverse 1 by s minus 2 is e raised to 2t. This plus is here. Then take 4 outside, 4 into 1 by s minus 2 the whole square. That means s is shifted to 2 units. That is the effect of e raised to 2t in time domain. So e raised to 2t. When we put e raised to 2t here, these 2 can be exempted from this position. So 1 by s square, only 1 by s square. L inverse of 1 by s raised to n is equal to t raised to n, s raised to n plus 1 equal to t raised to n by n factorial. We subtract 1 from these 2. So 1, t raised to 1 by 1 factorial. So simplified form is constant 4 into shifting effect e raised to 2t into Laplace inverse transform of 1 by s square, that is t. Okay, minus constant 7, L inverse of 1 by s minus 1, that is e raised to 1t, e raised to t. In these two terms we have 4 e raised to 2t common. 4 e raised to 2t into, here we have 1, here we have t, minus 7 e raised to t. So the solution is y of t is equal to 4 e raised to 2t into 1 plus t minus 7 e raised to t. Next idea is solution of ODE with shifted initial points. Actually, in time domain, we start the stopwatch from 0th state. So initial value of time is always 0. But in some situation we cannot take the initial measurement. In that situation we are forced to measure the values of y and y dash etc. at a particular time which is not 0. That is, initial timing need not be 0 in all cases. Such situations can be solved with the help of a Laplace transform. Usually in time domain we consider initial value 0. In some cases the starting time need not be 0. This means initial value problems with initial conditions given at some time t is equal to t not greater than 0 instead of t equal to 0. In such situations, this is the transformation. We put this t as t tilde plus t naught. That means t is replaced by t tilde plus t naught. Now the variable is changed to t tilde. Then when we put t tilde is equal to 0, we got t is equal to t naught. That is our original problem. The problem come to the original form. So this simply means we replace t by t tilde plus t naught, or we put the transformation t tilde plus t naught in the place of t. So for example, consider this simple problem. Solve the initial value problem y double dash plus y is equal to 2t with initial conditions y of pi by 4 is equal to pi by 2 and y dash of pi by 4 is equal to 2 minus root 2. Look, we expect y of 0 and y dash of 0 to solve a second order initial value problem. But I got y of pi by 4 and y dash of pi by 4. So t naught is equal to pi by 4. Here it is different from 0. So we use the transformation t is equal to t tilde plus t naught. T naught is pi by 4 here, t tilde plus pi by 4. Now when t tilde is equal to 0, that means y of 0 becomes pi by 4. Y of 0 is equal to y of pi by 4. That's all. Remember, the difference is, in the previous case we have do the problem in t variable. Now we put the transformation t equal to t tilde plus t naught. So automatically the variable becomes t tilde. That is the difference. And finally, when we finish the solution, we have to replace t tilde by t minus t naught, that is t minus pi by 4 at the end. So solution, as usual we write the given ODE with a transformation. Instead of t I put t plus t tilde plus t naught, t tilde plus pi by 4. When we simplify the right side, we got 2 t tilde plus 2 into pi by 4, that is pi by 2. Apply Laplace transform on both sides. So y double dash, so s square into y bar of s minus decrease the power of s by 1, so s raised to 1, that is s into second term always associated with the y of 0 minus power of s decreased by 1, s raised to 1 minus 1, that is s raised to 0 or 1, y dash of 0. Remaining time is y plus y bar of s equal to 2 into. We can think of Laplace transform of t tilde is equal to similar to Laplace transform of t. In s domain there is no more variable, only s. There is no s tilde like that. So Laplace transform of t tilde is 1 by s square plus 2 into pi by 4, that is pi by 2 into L of 1. L of 1 is 1 by s. Now we substitute the initial conditions and club the terms of y bar s together. Y bar of s of, here we have s square, here plus 1, so s square plus 1 into y bar of s. We know y of 0 is equal to y of pi by 2 itself, pi by 4 itself, that is equal to s into pi by 2 minus s into pi by 2 minus y dash of 0 is 2 minus root 2. Now we keep this term y bar of s into s square plus 1 on LHS and put all other things to the right side. So in the right side, s2 by s square plus pi by 2 by s. This minus term become plus when we move on to right. So plus pi by 2 into s. This minus of 2 minus root 2 changes to plus root 2 minus root 2. Then divide the entire term divided by s square plus 1. That means solve for y bar of s. Y bar of s equal to 2 by s square into s square plus 1 plus pi by 2 by s into s square plus 1 plus I put this pi by 2 to numerator, pi by 2 s divided by s square plus 1 plus 2 minus root 2 divided by s square plus 1. Now we have to take L inverse on both sides. Applying L inverse on both sides, we got, I am applying one result here. L inverse of, I take this 1 by s square as a single term into s. So L inverse of, this is f bar of, L inverse of f bar of s by s is equal to integral L inverse of f bar of s by s square is double integral. I use it here. Here I have s square, so I hide this s square. Effect of s square in the denominator is double integral. Integral 0 to tau to t tilde, integral 0 to t tilde. 2 is a constant, I take it here. Then this effect of s square is in this double integration. Remaining term is 1 by s square plus 1. So L inverse of 1 by s square plus 1. I am taking L inverse on both sides. Since there are two integration, we have two integration variable d tau plus constant is pi by 2. I take pi by 2. Here is 1 f bar of s by single s, division by single s. That means one integral s to infinity, 0 to t tilde. So when we write this integration, we can hide this s. Remaining portion is L inverse of 1 by s square plus 1. L inverse of 1 by s square plus 1. This d tau is for this integral. Next is pi by 2 is a constant. Take it here. Then L inverse of s by s square plus 1. And last term, 2 minus root 2 is a constant. 2 minus root 2 into L inverse of 1 by s square plus 1. L inverse of 1 by s square plus 1. Now we evaluate this. For simplicity, I consider these L inverses. L inverses of 1 by s square plus 1 is sin t. I write sin t. Sin tau here because integration variable is tau. Again, L inverse of 1 by s square plus 1 is sin tau. For 1 pi by 2, integral 0 to tau, t tilde. Here L inverse of s by s square plus 1, that is cos t. So pi by 2 into L inverse of s square by s square plus 1, that is cos 2. Then 2 minus root 2 into L inverse of 1 by s square plus 1 is sin t tilde. Now we have to evaluate this integral. First we try to find this integral, then this is one more integration of this result. Integral sin tau is equal to minus cos tau. So there should be a minus here. Then we have to substitute the limit. Upper limit is tau. So cos upper limit is t tilde. Sin t tilde, cos t tilde. Integral of sin is cos t tilde minus lower limit is 0. Cos of 0. Cos of 0 is 1. So we have a minus here, minus of cos tilde minus 1. I put this minus into the inside of this bracket. So 1 minus cos t tilde. So pi by 2 into 1 minus cos t tilde. Here we have to integrate this term again with respect to tau. So we got t tilde 1, integral of 1, that is t tilde. Integral of cos is sin t tilde. That's all. We integrate this once again. The limiting operation will follow. Next step is a simplification step. 2 into 2 tilde minus 2 into sin t tilde. Here we have 2 into plus sin t tilde. So that terms get cancelled. Pi by 2 into 1, pi by 2. I write pi by 2. Then pi by 2 into cos t tilde plus pi by 2 into minus cos t tilde plus pi by 2 into cos t tilde. There is a sign difference. It will get cancelled. It will become 0. So minus pi by 2 cos t tilde plus pi by 2 cos tilde becomes 0. Here only this minus root 2 into sin t tilde remaining. Minus root 2 into sin t tilde. So y of t tilde is equal to 2 tilde plus pi by 2 minus root 2 sin t tilde. That is the only thing we have to keep in mind. The variable is t tilde, not t, because we put transformation. And finally we have to replace this t tilde by t minus pi by 4. That's all. Because we put t is equal to t tilde plus t naught. Now we have to replace t tilde. So t tilde is equal to t minus t naught. T naught is our pi by 4. I substitute. So when we substitute t tilde in terms of t, the left side the function becomes the right side become a function of t. So instead of y of t tilde we can write y of t. That is why I put y of t here. Then 2 into t minus pi by 4 plus, there is no change to this pi by 2, minus root 2 into sine of t minus pi by 4. 2 into t, 2t minus pi by 2. 2 into pi minus pi by 4 is minus pi by 2 plus pi by 2 minus root 2 into. This is of the form sin a minus b. Sin a minus b is sin a sin b minus, sin a cos b minus cos a sin b. Sin a minus b equal to sin a cos b minus cos a sin b. Here b is pi by 4. both sin pi by 4 and cos pi by 4 are equal to 1 by root 2. So we can take 1 by root 2 from both the terms outside. So root 2 into 1 by root 2 get cancelled, we got 1. So sin t minus cos t minus root 2 into sin t minus cos t. Sorry, minus of sin t minus cos t. When we multiply this bracket inside to the bracket, we got cos t minus sin t. So final answer is y of t equal to 2t plus this pi minus pi by 2 gets cancelled, cos t minus sin t. That's all. By a proper substitution or using a proper transformation, our initial value problems with the non-zero t values can also be solved with the help of Laplace transform. So Laplace transforms are very useful in some mathematical and also in engineering area. So in this lesson, the main important takeaways are: 1. An infinite integral can be expressed in the form of a Laplace transform. Once an integral can be represented in the form of a Laplace transform, we can evaluate the transform, and so we automatically get the result. That's all. Then ODE can be solved using Laplace transform without much difficulty. There are two types of ODE: one initial problems, value problems with a zero initial time, and there is a time shifting initial value problems also. Anyway, I think Laplace transform is so more appealing to engineering community because of its applicability. Sigmoid functions are most prevalent function in engineering. Its area, in many cases we have to find the area under that particular curve generated by sigmoid function. In usual method it may not be easy, but in the case of Laplace transform, that is as simple as evaluating a Laplace transform. So that's all about the applications of Laplace transform in an examination viewpoint, and also some basic knowledge level understanding. Okay, thank you very much. Thank you for patient listening, and thank you very much for spending this much time with me. Thank you.